Section: Introduction. In this section, we delve into the challenges and innovations surrounding the deployment of very large language models, often abbreviated as LLMs. Despite the progress in making these models smarter and more efficient, their practical use is still limited by the high computational demands they require. One of the main issues is the way these models generate text, one piece at a time, which doesn't fully take advantage of modern computing hardware designed for handling many calculations simultaneously. This sequential process, known as autoregressive generation, contrasts with a more efficient method where all parts of the input are processed at once, which we refer to as prompt processing. We also explore an interesting question: how much of a language model's capacity needs to be dedicated to understanding the input versus generating a response? Currently, the models that only generate responses without separate understanding mechanisms might not be using their capacity in the most efficient way. To investigate this, we introduce a new design called Tandem transformers. This design splits the task into two parts. A larger model focuses on understanding the input, while a smaller model takes on the job of generating the response. The smaller model starts by generating a set number of words, then waits for the larger model to process these before continuing, and this cycle repeats until the full response is generated. We also add a special layer to help these two models work together despite their differences in size. Our experiments with different sizes of tandem transformers show that it's indeed possible to separate the tasks of understanding and generating without losing accuracy, and even speeding up the process. For example, when comparing our models on a standard dataset, we found that our approach not only speeds up the response time but also maintains a high level of accuracy, even outperforming some larger models. We contrast our tandem transformers with other approaches that either encode the input first and then generate the entire response or try to speed up the process by generating multiple parts of the response at once. Our method stands out because it doesn't need to generate a draft that the larger model then corrects, making it more efficient. Additionally, we introduce an enhancement called Tandem plus Speed, which uses the smaller model to create a draft that the larger model quickly checks, further improving speed without sacrificing accuracy. Our extensive tests, especially on the latest TPU hardware, show that our tandem transformers, especially when combined with the speed technique and further optimized with techniques like logit distillation, can significantly outperform traditional models in both speed and efficiency. We also find that adjusting the number of words generated in each cycle can further reduce response times. In summary, our main contributions are the development of the tandem architecture, which efficiently divides the tasks of understanding input and generating responses, the tandem plus speed technique, which further speeds up response generation, the introduction of an adaptive block length to optimize performance, and comprehensive testing that demonstrates the effectiveness of our approach, particularly in terms of speed, without compromising the quality of the output. Section Summary. In this section, we introduce tandem transformers, a novel architecture that focuses on separating the capacity needed for prompt processing, NLU, from response generation, NLG, in large language models. By allocating more model capacity to prefill processing compared to response generation, tandem transformers aim to maintain high-quality response generation efficiently. Through experiments, we demonstrate that tandem transformers, especially when combined with the speed framework, can significantly reduce inference latency while maintaining output quality, showcasing its potential for practical applications. Section: Outline of the paper. In this section, we outline the structure of our paper. We start by reviewing related work in the field. Next, we introduce the main concepts and the design behind the tandem transformers architecture. Following that, we share the results of our experiments with tandem transformers. We wrap up by discussing potential future research directions. In the realm of related work, we delve into encoder-decoder models first. These models are particularly popular for tasks like machine translation. Due to the computational challenges posed by autoregressive decoding, there's been interest in combining a large encoder with a smaller decoder. Our contribution is an extension of this idea, applying an encoder-decoder framework within the decoder itself. We also explore mixture of experts, MO, and sparsity-based methods, which aim to optimize the inference cost of large language models, LLMs. These methods are not in competition with our approach. In fact, they can be integrated. For instance, both the larger and smaller models in our architecture could employ MO or sparsity techniques. Another area we touch upon is distillation. This process involves training a smaller model using the outputs, logits, of a larger model as targets. Our approach can be seen as a broader application of distillation to transformers, where the smaller model can access representations from the larger model for previously processed tokens. Our experiments demonstrate that our method not only complements traditional logit distillation but also enhances it. We also discuss speculative decoding, speed, a strategy designed to reduce the inference time of LLMs without compromising their quality. We show that tandem transformers can be effectively incorporated within the speed framework, offering significant improvements. Among various drafting strategies explored in speed, distillation-based ones have shown the most promise, and our tandem architecture further boosts their performance by providing a more efficient drafting process, thereby reducing latency. Moving on to the tandem transformers section, we describe the architecture, training, and inference processes of tandem transformers. A standard decoder transformer processes a sequence of tokens, with each token being transformed through layers of attention and feed-forward operations. Notably, the attention mechanism here is causal, meaning each token only interacts with preceding tokens. The tandem transformer model consists of a primary, larger, model and a secondary, smaller, model. The primary model processes tokens similarly to a standard decoder transformer. We introduce a block length parameter and layer numbers for both models, along with a layer assignment function that maps layers from the secondary model to the primary model. The secondary model then attends to the primary model's representations for tokens from previous blocks. This process involves transforming the primary model's token representations into formats suitable for the secondary model, using both attention and feed-forward operations within the secondary model. The final output comes from the last layer of the secondary model. It's important to note that the primary and secondary models can differ significantly in terms of scale parameters and attention mechanisms. In our experiments, we use linear projection layers for transforming representations between the models. Section Summary. In this section, we introduce the organization of our paper, including a review of related work, the design of tandem transformers architecture, experimental results, and future directions. We discuss how tandem transformers extend the concept of encoder-decoder models by incorporating a large primary model and a smaller secondary model that leverages the primary model's representations for tokens from previous blocks. This architecture aims to improve inference efficiency and reduce latency, showcasing its potential within frameworks like speculative decoding, speed. Section: Training. In this section, we discuss how we train our model. We start by dividing the training data into blocks, each containing a certain number of consecutive tokens, which we refer to as gamma. When predicting a specific token within a block, we use the tokens that came before it as input to our secondary model, denoted as M_S. It's important to note that within the attention mechanism of M_S, it computes key-value pairs for all preceding tokens in the current block by itself. However, for tokens in earlier blocks, these key-value pairs are calculated by our primary model, M_L. We then use a special layer to make sure the data from M_L fits well with M_S. We experiment with different ways of training our tandem transformers. In one approach, we only update the secondary model, M_S, and a specific layer called the tandem feedforward layer, while keeping the primary model, M_L, unchanged. The loss, which is a measure of how well the model is doing, is only calculated based on the output of M_S. In another method, we train both M_L and M_S models and apply the loss to the output of M_S. We also try a third approach where we train both models but calculate the loss based on the outputs of both M_L and M_S. To make our training process more efficient, we start with pre-trained models for both M_L and M_S and then continue to train them together for a few more steps. Specifically, we use models known as POM2 Bison and POM2 Gecko as our starting points for M_L and M_S, respectively. We find that keeping the primary model frozen while training only the secondary model gives us the best accuracy. We introduce two versions of our model based on how we calculate the loss. The first version, which we call Tandem CE, uses a standard loss calculation method focused on the secondary model's output. The second version, Tandem Distill, aims to improve the quality of M_S by also considering the predictions of the pre-trained M_L model when calculating the loss. This second version shows better performance than the first. When it comes to using our model to make predictions, the process starts with M_L processing the initial input and generating data for all input tokens. M_S then uses this data to generate a response, one block at a time. M_S pays attention to the data generated by M_L, ensuring that the information flows correctly between the two models. We explore two different setups for generating responses. One where M_L also predicts the next token, and another where it only generates data for M_S to use. We also make sure that our model can handle different block sizes during the prediction phase, even though it was trained with a fixed block size. This flexibility allows us to use our model more efficiently, especially on powerful computing hardware. Our tests show that our model can adapt well to different block sizes, indicating its robustness and versatility. Section Summary. In this section, we partition the training sequence into blocks based on a block length parameter gamma and explore different training configurations for tandem transformers. We find that initializing the primary and secondary models with high-quality pre-trained checkpoints and using the primary model frozen approach yields the best accuracy. Additionally, during inference, the primary model processes the prompt and generates representations for all prompt tokens, while the secondary model auto-regressively generates response tokens, attending to the primary model's representations. Section: Tandem plus Speed. Tandem in the speculative decoding framework. In this section, we delve into the integration of tandem transformers within the speculative decoding framework known as SPEED. SPEED addresses the inefficiency found in autoregressive generation by employing a smaller, secondary model to draft tokens and a larger, primary model to verify these tokens. This ensures that the quality of the output is on par with that of the verifier model. However, the success of SPEED largely depends on the drafter's ability to produce long and accurate sequences of draft tokens. Our tandem transformers are perfectly suited for this setup, with our secondary model acting as the drafter and our primary model taking on the role of the verifier. When using a tandem model, we first utilize our primary model to process the initial query or prefix and to create representations for them. Following this, our secondary model takes over and drafts a sequence for the first few tokens, doing so one after the other. The primary model then checks this sequence all at once, pinpointing the first instance where a drafted token doesn't match its expectations. If all tokens are verified successfully, this point is just beyond the last drafted token. At this juncture, we adopt the output from the large model for the token at the identified location, and our secondary model resumes drafting tokens from the next position, utilizing the representations of all preceding tokens from the primary model. This cycle repeats until we've generated a complete response. We can extend this method to generate multiple complete responses for the same query, a process we refer to as num samples. This allows us to later rank these responses and choose the best one. It's worth noting that the point at which a token is rejected may vary across the different samples being generated. This approach can also be scaled up to handle larger batch sizes, meaning we can process multiple queries at once. In practice, systems might use both num samples and batch size greater than 1. But the improvements in latency with tandem plus speed are primarily influenced by the overall batch size, which is the product of num samples and batch size. For simplicity, we focus on scenarios where num samples is greater than 1 and keep the batch size fixed at 1. We also introduce an adaptive approach to determining the length of the block of tokens to be drafted and verified, as opposed to the fixed block length used in standard speed. We train a relatively small two-layer multi-layer perceptron, which we call the router MLP, to predict whether the current token drafted by our secondary model is likely to be accepted by our primary model. At each step, we compare the router MLP's prediction against a set threshold to decide whether to proceed with verification by the primary model or continue drafting with the secondary model. The router MLP bases its predictions on several inputs, including the secondary model's uncertainty about the current token, the probabilities of the top few most likely tokens, and the model embeddings for these tokens. We train the router MLP to predict the likelihood of disagreement between the secondary and primary model's outputs for each token, using a measure known as total variation distance between the output logits of the two models for comparison. In our experiments, we evaluate the performance of tandem transformer models. Except for the novel architecture of the tandem transformers, we generally adhere to the same training protocols previously established, including the use of the same training dataset and optimizer, among others. For further training details, both of our tandem models, Tandem CE and Tandem Distill, start with the secondary model initialized as the pre-trained POM2 Gecko, while the primary model is kept as the pre-trained POM2 Bison, without any changes. The projection or tandem feed-forward layers are linear and are initialized randomly. Both models are trained with a block length of 2 tokens. Within the speed framework, we evaluate a version of POM2 Gecko that has been trained using logit distillation, named POM2 Gecko Distill, which is based on the initial POM2 Gecko model. This distillation process is similar to the second phase of training for the Tandem Distill model, as distillation has been shown to enhance the performance of secondary models in speed. For the adaptive block length feature in speed, we train a small, two-layer MLP model to assess whether the current token drafted by the secondary model will likely be accepted by the primary model. We set a threshold of 0.8 to determine if the secondary model should continue generating additional tokens. Section Summary. In this section, we introduce the tandem transformer models, where a smaller drafter model generates draft tokens and a larger verifier model confirms them to improve autoregressive generation efficiency. The tandem framework involves the secondary model as the drafter and the primary model as the verifier, with a process of generating and verifying tokens iteratively until a full response is produced. Additionally, we implement an adaptive block length approach using a small MLP model to predict token acceptance by the primary model, enhancing the drafting process within the speed framework. Section: Performance Evaluation. In this section, we delve into how we assess the performance of our models, Tandem CE and Tandem Distill, by comparing them with various other models like POM2 Gecko, POM2 Gecko Distill, POM2 Otter, and POM2 Bison. We look at their performance across a range of tasks and also examine how quickly they can operate, which we refer to as latency. For evaluating how well our models do on specific tasks, we test them on a variety of benchmarks. These include superglue, Tydeka, and a large set of tasks we call Gen tasks, which includes SQUADV2, natural questions, trivia QA, web questions, and Lambda. We also look at MBPP and WMT22, with the WMT22 results being an average of translations from various languages into English. For Tydeka, we include the gold passage in the input and report the average F1 score across all languages. For both superglue and Gen tasks, we stick to previously described experimental setups and report average results. All these evaluations are done with just one example provided to the model, known as one-shot evaluations. When it comes to latency, or how fast our models can generate outputs, we test them in 2 different scenarios. First, we use Tandem CE and Tandem Distill as secondary models within a framework we call Speed, with POM2 Bison being the primary model. It's important to note that Speed ensures the output quality matches that of the primary model, POM2 Bison. We compare these setups against using PaLM-2 Bison by itself and also against a setup where PaLM-2 Bison is the primary model and PaLM-2 Gecko Distill is the secondary model within Speed. In the second scenario, we look at how Tandem CE and Tandem Distill perform on their own, comparing them to PaLM-2 Gecko, PaLM-2 Otter, and PaLM-2 Bison. All these tests are run on a specific type of processor, the TPU-v5e, and we evaluate latency using test sets from CNN Daily Mail, Reddit post summarization, and 1,000 prompts from the 1 billion word benchmark. We report latency for both single samples and batches of 4 samples. Now, let's talk about what we found. In terms of pre-training metrics, our tables show that tandem transformers not only perform better than just using logit distillation but also that combining logit distillation with tandem transformers further boosts performance. When looking at latency within the Speed framework, our results clearly show that tandem models, especially when used as secondary models, can speed up the process compared to just using PaLM-2 Bison or PaLM-2 Gecko Distill as the secondary model. This improvement in speed does not come at the cost of output quality, thanks to the guarantees provided by the Speed framework. Evaluating the Tandem model as a standalone entity, we find that it significantly enhances performance on downstream tasks compared to the baseline models and is almost as good as the PaLM-2 Otter model. In some cases, it even comes close to the performance of PaLM-2 Bison itself. Moreover, the Tandem model operates about 1.16 times faster than the PaLM-2 Otter model, making it an attractive option for standalone use. Lastly, we introduce an approach to further enhance the Speed framework's performance by using adaptive block lengths, which we refer to as adaptive gamma or AG. This method involves using a small, cost-effective router to decide whether to continue with the secondary model or check the generated tokens with the primary model after each token prediction. Our findings show that this approach significantly reduces the number of times the secondary model is run while slightly increasing the primary model runs. This demonstrates the effectiveness of using adaptive block lengths, as it greatly reduces the need for secondary model runs without much increase in primary model usage. Section Summary. In this section, we compare the performance of Tandem CE and Tandem Distill with other models on various downstream tasks and latency metrics. We evaluate these models on Superglue, Tidica, GenTasks, MBPP, WMT22, CNN Daily Mail, Reddit post summarization, and 1 billion word benchmark. Our results show that tandem transformers outperform logit distillation, and combining it with tandem transformers further enhances performance without compromising quality. Additionally, when used within the Speed framework, tandem transformers demonstrate significant speedups over primary models like PaLM-2 Bison, making them promising for standalone deployment. Section: Deep Tandem Transformers. In this section, we explore a novel approach called Deep Tandem Transformers. In this method, we use a large model, which we'll refer to as M_L, and a smaller model, M_S, working together in a unique way. Instead of processing everything in sequence, M_L sketches out a preview of the upcoming block of tokens all at once. Meanwhile, M_S takes on the task of generating the actual sequence of tokens, one after the other, based on the sketch provided by M_L. To get into the specifics, the large model M_L creates an initial representation for a block of tokens. This representation is essentially a draft or a sketch of what the next few tokens could be. Then, we take these sketches and combine them with the representations of previous tokens. This combined information is then fed into the smaller model M_S, which predicts the next token in the sequence, doing so one token at a time. The final output of our model is the prediction of each token in the input sequence, as determined by M_S. We've illustrated this process in a figure within the paper to make it easier to visualize. Moving on to our experimental findings, we tested the deep tandem transformers against the standard architecture. For this experiment, we used models from the Lambda family, specifically a model with 1 billion parameters. We divided this model into 2 parts, with 8 layers each for m_l and m_s, and set the block length to 2 tokens. The results, which we've detailed in a table, show that this setup results in only a minimal loss in performance, even though the autoregressive component is not the sole method of generation. We also delve into the importance of the smaller, autoregressive model, m_s. By comparing a block prediction model, where we predict a block of 8 tokens at once, to a fully autoregressive model, we observed a significant difference. The block prediction model, which relies on the large model's output to predict the next token, showed a much higher cross-entropy loss compared to the fully autoregressive model. This comparison, presented in another table, highlights the effectiveness of including the autoregressive component in our tandem setup. In summary, our exploration into deep tandem transformers demonstrates a promising approach to leveraging the strengths of both large and small models. By having the large model sketch out future tokens and the small model refine these predictions, we achieve efficient and effective token generation with minimal performance loss.